today we'll be talking about an all-new class of functions today, and we're going to start with exponential functions. These are a little bit different than anything that we've worked with before. This is our first new function that's called a transcendental function, and transcendental functions behave and are solved a little bit differently than anything that we've done before. So first of all, what makes something an exponential function is if you'll notice that in all of the other equations that we've solved, x has been a variable on the bottom, right? It's not been raised in this particular case, and all exponential functions. What makes them exponential is that the x is actually the exponent, making it an exponential function. Okay, so x is the exponent. Like the other ones that we've looked at, we've done a lot with y equals x squared, where I have an x and an exponent, but they're switched, right? So x is the base, and 2, a number, is the exponent. So we have the opposite situation here, where I have a number as my base and x as my exponent. So this is what makes it exponential. Now, we're just going to plot this a little bit by hand, really. And I know that I have this kind of going in the opposite way. Usually we start with the smallest numbers up here, but the easiest ones are to put in the whole numbers first. So I want to just talk about how these negative exponents work, just in case you've forgotten. So first of all, if I put in 2 to the first, this is fairly simple. This is just 2, right? 2 to any power, 2 to the first power is 2. Any number to the first power is itself, right? So then if I put in the 2 for this case, then I have 2 squared, which is 4. And then if I put the 2 in here, I get 2 cubed, which is 8, right? Okay, so let me just plot these really quickly. So if I put in 1, I get out 2. If I put in 2, I get out 4. And if I put in 3, I get out 8. Okay? So this piece over here looks like this, okay? Alright, so now we come to the 0, and I put in 0, and I get 2 to the 0, okay? So if you check out your calculator, any number to the 0 power is always equal to 1. So I have the point 0, 1 here. Actually, it's here, not there. Okay, so there we go. We'll connect it here. Ignore that extra little point there. And now we come to the negative powers. Okay, now I can't say this enough times. Negative powers do not give me negative solutions. In fact, there's no way for me to get a negative solution out of this, because if I raise a positive base to a power, I'm never going to get a negative number. So 2 to the negative 1 really is the same as 1 over 2 to the first. So this gives me a half. So at negative 1, I get a half. Right here is approximately, okay? And then if I put in negative 2, I get 2 to the negative 2, which is really 1 over 2 squared, which is 1/4. Okay? So it comes down a little farther, and then by the same reasoning, 2 to the negative 3 is 1 over 2 cubed, which is 1 over 8. Okay? And so this goes on and on and on like this. As long as I put in a bigger number, or a more negative number I should say, it goes like in this direction. So this is our first exponential function that we've looked at. Okay, so some of the things I'd like to point out here. The common question that we're always being asked is, what is the domain of this function? Well, I can tell just from looking at the graph, it's definitely right. It's going to arrow out in this direction. It's going to cover completely from side to side. Now, when it comes over here, it's going to be way up, right? Way up here. But it will. There's no number that I can put in here for x that my calculator would spit out. Ooh, I don't know what that means. Okay, so the domain is all real numbers, or I'll write it in interval notation as in negative infinity to infinity. Right? I can write it like that. I can write all real numbers, of course, as usual. Okay, so next question is my range. So just looking at my range, I notice that I'm not really hitting the x-axis here, and I won't. Although my calculator, if I put in a bigger and bigger number, right, for my negative exponent, if I have 2 to the negative 50, my calculator is going to approximate that as 0, but it never technically reaches x equals 0, or the y equals 0. Okay, so even though our calculator would probably say it's, it would round to 0, it never actually touches. So this actually is a horizontal asymptote, right? So it y equals 0. Right, so my range is completely up above, right? So when I'm looking for range, I'm looking for y's. Where does my y's go? Well, the smallest value is 0, and I'm going to say 0 with an open parenthesis, right? And up to infinity, right? Or as an inequality, that would be just x is greater than 0, okay? Or I'm sorry, y is greater than 0, because we're talking about range and not domain, okay? All right, so then let's talk about the end behavior, right? And limit as, or not limit. Well, we can talk about limits now, haven't we? We've done that. So as x goes to infinity, so as x gets really big this direction, right? What is my y value doing? It's shooting straight upward. So as x goes to infinity, f of x also goes to positive infinity. Or now, since we've done a little calculus, we could say that the limit as x goes to infinity of f is infinity. That's another way of writing it, if we've had the calculus. And then as x goes to negative infinity, what is f of x doing? Well, f of x is flattening out on this side, and it keeps getting closer and closer and closer to 0, right? So as f of x, or as x goes to infinity, f of x is going to 0. Or we could say, in calculus writing, as the limit approaches, as the limit as x approaches negative infinity of f is equal to 0. Okay. All right. So something to point out here about my graph, okay, is that this is always increasing. So from over here, my graph is, it's increasing pretty darn slowly over here. It almost looks horizontal, but it is increasing, and then it comes up here, and then it really takes off and increases. Okay. And I've already talked about y equals 0 is the horizontal asymptote. Okay, so now this is an example of, this is what we call an exponential growth, right? So that's my big words at the bottom. This is an exponential growth. What makes something an exponential growth? Well, an exponential growth would be when my base, right, so this number, which is the 2, right, so the 2 is my base. If my base is bigger than 1, right, or actually, so if I call this y equals b to the x, then that means that b is greater than 1, okay? My base here, that's why I used b. So if I'm using this kind of notation, as long as this number is bigger than 1, I'm going to get this behavior. Now, you have to be careful, because I know a lot of textbooks like to write like y equals 2 to the negative x. Now that looks like I have a base of 2. But actually, this is a little bit of a trick, because what did we learn from this over here with our negative exponents? That y equals 2 to the negative x is actually y equals 1/2 to the positive x. Okay, so this negative sign, it just means the reciprocal. And so we have to make sure, 1, that our x is positive, and 2, that our base is bigger than 1. And then we will get this sort of behavior where it grows. Okay? All right, so now we've talked about how we can write 2 to the, so this y equals 1/2 to the x can also be written as 2 to the negative x. And I thought we would take a quick peek at this graph as well. All right, so if I plug in 1 into 1/2 to the x, I get 1/2, right? So I'll get 1/1/2 maybe there. If I plug in 2, I get 1/4, right? Because I'm going to have 1 squared over 2 squared, which is 1/4. So I'm going down a little bit further. If I plug in 3, then I get 1/2 cubed, which means I have 1 cubed, which is 1, over 2 cubed, which is 8. And so my graph kind of looks like this. Now if I plug in 0, again, any number to the 0 power is in fact 1. So I know I'm going to have this point here. All right, and now my negative exponents. So now when I plug in 1/2 to the negative 1, this is really like 2 to the positive 1, or you can think of it as 2 over 1, right? It's the reciprocal of 1/2. And so I end up with 2 on this side. Alright, so if I plug in -2, that means I have 1/2 to the -2, which really means I have 2 to the +2. So this gives me a value of 4. And you might notice that basically I'm getting exactly the same values as I got before, just in the opposite direction. So now I have 1/2 to the -3, which really means I have 2 to the +3, which gives me 8. So that means my last point up here is somewhere up here. And so my graph looks like this, right? It actually just looks like it's kind of like and it is actually, it's a reflection over the y-axis here, because just like, remember when we were doing graphing transformations, right? If I had y equals x squared, and then I put, well, that's not a good example. Let me try the square root of x. If I put in negative square root of x, like, actually I'm not doing very well right now. So if I have y equals, and I have the minus sign underneath here, like it is with this x here, then what ends up happening is my graph of, right, it looked like this, now it does this, if you recall back in when we were doing graphing transformations. So this is a reflection into the y-axis, and essentially that is what happened. If I compare these two kind of side by side, right, they're just reflections of each other over across the y-axis. Okay, so now my domain in this case, again, my domain didn't change, right? I mean, my graph might be pointing in different directions, but it's still going to cover side to side. So my domain here is all real numbers, or from -infinity to infinity, or however you want to write all real numbers. My range hasn't changed if I look at them side by side, right? They're all both completely up above the x-axis, meaning that my range would be y is greater than 0. And it's not going to touch, so I'm going to say strictly greater than. Now I have opposite behavior here, right? Because as x went to infinity for this graph, y went to infinity, or f of x went to infinity, but in this case, I've got the opposite behavior going on. As x goes to positive infinity, y, or f of x, is approaching 0. Right? And again, we could write the limit as x goes to infinity of f is equal to 0. Alright, so then as x goes to -infinity, right, I have the opposite behavior. I'm going off to positive infinity. And so I could also write that the limit as x approaches -infinity of f is positive infinity. Okay, so now in this case, right, this graph over here was always increasing. This one is decreasing, right? It's completely, if I connected 2 points on this with a straight line, they would have like a negative downward slope, right? And then also the horizontal asymptote didn't change. It's still the x-axis here, the equation y equals 0. So this is what we call a exponential decay, and we end up with an exponential decay, right? If we have our x to a positive, right, our x is a positive, and this number is between 0 and 1, we get this exponential decay. So if we think of it as y equals b to the x, then when b is between 1 and 0, right, we get this exponential decay, assuming that our exponent is positive, right? So that's the standard. So when the exponent is positive, when this number is between 0 and 1, I get a graph that looks like this. When my x is positive and my number is bigger than 1, then I get the opposite behavior. Okay. So again, things that make it an exponential function are the fact that the variable is the exponent. Okay. We're going to solve equations later using these, and it's a completely different method than what we have used so far to date. Right. And I just wanted to show you really quickly on Desmos. I have it kind of set up here. If you can see it, let me. Okay, so I have this set up. There, you can kind of see it. I have y equals b to the x, and I have my slider here set that b equals 0, which when b equals 0, I don't really have an exponential function. That's why it's looking like a flat line. but I've got this set to just go between b equals 0 and b equals 1. So let me just run my video, right? So again, my x is a positive power, and as long as my b is bouncing between 0 and 1, I get this exponential decay. Just trying to reinforce this again, and you can play with this yourself if you'd like. Okay, so now let me stop that, and let me instead go from 1 to, I don't know, 10. Okay, and let me run this one. Okay, so this time when my b is positive, right, my b is bigger than 1, or at 1 actually I get that horizontal line, because really then I'd have b to the 1, which is just y equals b, which is just the line, a horizontal line, so that's why it kind of flattens out there for a flash. But then it just becomes, it just keeps, the bigger my b becomes, the more basically closer to the top comes to my y axis. Okay, so just kind of re-emphasizing that's how that behaves. Alright, so let's look at how we can, let's talk about these for a little bit. We're going to kind of stray off the course a little bit here, and let's talk about, why do we use these exponential functions and how do they work. Okay, so let's say we have a starting salary of $35,000. Okay, and we'll be optimistic, maybe, sort of, and say we're going to get a 2% increase in our salary every year. Okay, and we want to figure out what's our salary going to be in 3 years. Okay, so let's think about this for a second. How would we figure this out? Okay, well, our starting salary is $35,000, right? And then we're going to add 2% of $35,000 to it, right? So that means whenever I say the word of, that means multiply, right? So I'm going to convert my 2% to a decimal first, right? So it would, as a percent, it would move back 2, right? So it's 0.02. It's like dividing by 100. And so I'm going to start out with 35,000, and then my first year I'm going to add 2% of 35,000. Okay. Now when I put this in my calculator, I end up with $35,700. Okay. So this is actually at the end of my first year. Or actually, yeah. So I guess this is, let's say in 3 more years. Okay, so this is basically after the first year, I'm going to end up with this. Now I would like to point out that if I leave it like this, I actually have 35,000, and I'm going to use my factoring skills here, and I'm going to factor out this 35,000. Okay, so when I do that, I have 2 things here. I should have 2 things in this parenthesis. So my first thing, 35,000 times 1 gives me this, and then plus, right, because I have a plus here, 35,000 I already have, plus 0.02, right? So I could write this as 35,000 times 1.02, right, because I can add the 1 and the 0.02. So basically, this is another way. I could just put this in my calculator. If I put 35,000 times 1.02 in my calculator, I also get $35,700. So I haven't changed it. I've just changed the way the equation looks a little bit. Okay, so now this is my second year salary, right? I'm just going to write it like this. I mean, I know that that's equal to this, but I'm going to write it like this. So I'm going to write, this is my start of my next year's salary, and I am going to then get another 2% raise. Okay, so that means I've got, this is my salary now, 35,000, and times 1.02, and then I'm going to multiply it by another 2%, right? So just like I did up here, this was my salary, and then I added my salary with 2%, right? So I'm doing the same thing here. This is now my new salary, which we know that is $35,700 really here, right? But I'm just putting this in here. Now when I put this in my calculator, did I calculate it? I think I came up with 36,414. Okay, so if we put it in our calculator like this and we add and multiply, then this is approximately what we should have. Now I want to show you again. Now I notice that in these two, I've got these 2 factors here. I have in common this is common with this, so I'm going to factor out that. So I have 35,000 times 1.02, right, multiplied by, now I'm just going to have a 1 here because I already have both of those here, and then I have, there I factored that out, and I have plus 0.02. So after my second year, I could really write this as 35,000 times, or 1.02, okay? Squared, actually, right? Because I have it here and I have it here. So this is my second year, which also, if I put that in, I should get the same value. I'm just trying to show you sort of like, this is kind of, see how the exponential function is working? So now if I do it for the third year, so this is, I know that these two things are equal, so this is my third year salary, so this is year 1, then this was year 2, this is year 3, so now I have my third year salary starts out as 35,000 times 1.02 squared, and then of course I'm going to add my 2% raise, so I'll have 2% of this. So again, I can put it out front, 0.02 times my third year salary, or my second year salary, I guess I should say. Alright, so I have this. Now I notice that they have this and this again in common, so I'm going to factor that out as 35,000 times 1.02 quantity squared, and when I factor that out, right, this one almost goes, I have both of these pieces, so I just need a 1 here, and then over here, this is the same as this, so all I need is the 0.02 here, and then I could write this as 35,000 times 1.02 cubed. And I don't actually think that I figured that out, but we can do that. So if I was going to put this in my calculator like this, what I would do is, depending on what kind of calculator I have, and I'm just using my phone calculator here, I'm going to actually put in the thing to, right, we always raise this to the power first, and it's a little bit easier to do that. So I have 1.02, and then I'm going to raise it to the third power over here, and then that's what that value is, and then I multiply it by the 35,000, and this is how I get my answer, which, so after 3 years I will now be making $37,142.28, okay? And I could keep going with this. So now I notice that basically my salary after X years will be, assuming a 2% steady increase, right? If it changes, then this doesn't work, but would be 35,000 times 1.02 to basically the year that I want, right? Because this is my salary after 3 years, and this was a 3. And so, like if I wanted to know what my salary was going to be after 10 years or 5 years, I could just put in the 5 here. Okay, so I would put in the 1.02 and then whatever key you need for your exponent. A lot of times it's a little caret key that looks like that. And then you put in your value there and then multiply it by the 35,000 and you get your answer. Okay, so one of the things that I want to point out just really quickly, a little bit of vocabulary, is that when you notice that actually the growth rate for this, right, even though I have this 1.02 in here, my growth rate was 2%. So it's kind of like this piece right here, that's my growth rate, okay? And then when I add it, the 1.02, so my growth rate is actually, in this case, 0.02, or we could say 2%. My growth factor would be the 1.02. Okay, oops, sorry. So my growth rate would be the 0.02 or 2%. My growth factor would be 1.02 or 102% basically of the previous one, right? That means I'm actually, it's more than what I started with. And then, let's see. So, and I also want to point out that this is actually when there's a number in front of my exponential, right? So the ones that I graphed before, the 2 to the x, those didn't have another number in front of them, but if I did, it would look like y equals 3 times 2 to the x, like that. then a lot of times we call this the initial amount, and that was, in this case, our initial amount was our starting salary. So sometimes populations are represented with exponential functions, and whatever this number is in front of the exponential, that would be like your initial population that you start with. Okay, and we will continue to talk about exponential functions next time.